Hello, this is Coach Meinbauer, and welcome to our AP Pre-Calculus video on 1.5 Day 2. 1.5 is a pretty hefty topic with polynomial functions with the zeros, and we add in complex numbers, other things as well. So we have 3 days on it. We're on Day 2, so let's get at it. Okay, so polynomial functions and complex zeros. We're going to talk about those complex numbers here in just a bit, but I do want to talk about what a zero is. As mentioned in previous videos, a zero is going to be the same thing as a root, which is the same thing as an x-intercept. So these are the same things as x-intercepts. So a zero is an x-intercept, which is the same thing as a root. Okay. Also, so if we have that a is a zero, then x minus a is a linear factor. So I'm going to kind of make some sense of this real quick. So if I know that we have f of x equals, I don't know, x minus 2. Okay? Well, if we set this factor equal to 0, we're going to get x equal 2. That is our 0. So this is a 0. And then x minus 2 is the linear factor. Okay, so just a little bit of technical terminology. I'll learn how to talk eventually. Okay, so again, if we have a 0, which is a root, and it talks about x-intercept right down here, we have an x-intercept at the point a comma 0. So you just kind of need to be able to put all that together. So let's go to our first example here. We have a polynomial function, p of x, which is something that we could factor. We're not going to factor right now, but we have negative x to the fourth plus x cubed plus 4x squared minus 4x. It's shown to the right. Super nice. They give us all of the x-intercepts. Okay, so they label first as negative 2, 0. So I'm going to go to my graph and kind of just label them as well. Get negative 2, we got 0, 0, we got 1, 0, and we got 2, 0. So we want to write this now as a function of product of linear factors. Okay, so here we go. So p of x is also, what is going on? There we go. So p of x is equal to, well, if I have x equals 2, so it's really, that's what I have. I have x equals negative 2. So that linear factor is going to be x plus 2, which is the opposite sign. I have x equals 0, so I'm going to have x minus 0. I'll fix that in a second because that don't look too pretty. I have x equals 1, so it's going to give me x minus 1. And then I have x equals to 2, so I'm going to do x minus 2. I just noticed that this is an increasing function that I just wrote this as. So I'm going to make this a little bit prettier. Since I have x minus 0, I'm just going to put that out in front, and I'll probably try to write this correctly. So I have x, x plus 2, x minus 1, and then x minus 2. Okay. I'm not done, by the way. So don't be like, well, you made a mistake, because I do make mistakes a lot. I'm not done yet. There is one little thing that I'm forgetting. But just getting the idea of linear factors, that's what we need right here, okay? So now, what's my degree of this? Let's just do a couple of checkings. What's my degree? So this is degree 4 right here. So D equals 4. It stands for degree. So it's degree 4. So if I count up all my linear factors, I should have 4 linear factors because those are 4 single powers. My leading coefficient is negative. So my A is equal to negative 1 in this case right here. So I need to make sure that my A matches up as well. Does my A match up here? It does not. So technically I'm missing a little minus sign right there. If I'm really be correct about it, I need my minus sign right there. Okay, and I know that because my end behavior, my right end behavior is negative infinity. Okay. Let's talk about multiplicity, which is going to build off of what we did in the previous set of notes. So multiplicity, if a linear factor is repeated n times in a factored form of a polynomial function, the corresponding real zero has a multiplicity of n. So easy way to describe this is let's just look at this example. Okay, I have 3 real zeros, 3 roots, 3 x-intercepts, whatever. And that's going to be at x equals 0, -3, and 2. And that says that for me. And how do I know that? Again, I'm just going to set each of these linear factors equal to 0. That's how I get these numbers right here. Now, multiplicity, that's going to be the degree that's on it. So what's the degree that's on just the x? Just a 1. So this has multiplicity of 1. For the x minus 3, I'm going to look at the degree of x plus 3. What's the degree of x plus 3? It's 4. Try the last one on your own. It's a 5. Okay, so sometimes we'll have to state what the multiplicity is. We need to know stuff like that. Okay, real zeros with even multiplicity. This was mentioned in our curve sketching. Anything that has an even multiplicity is tangent to the x-axis. You need to know that. Anything that has an even multiplicity is tangent to the x-axis. If you have a highlighter, highlight. So if we look at this example right down here, do you see any even multiplicities? If you're wondering, how do I find an even multiplicity? Where are we tangent on the x-axis? You have no clue what that means. In the notes I used last time, I said bounces. If something bounces, it's also tangent to the x-axis. So do you see any bounces there? Yeah, you totally do. Where's the bounce at? It's at 3. So 3 is multiplicity of 2, and the graph is tangent. I'm going to add that in right there on the bottom. Is tangent to the x-axis. Beautiful. Let's talk about odd multiplicities and what the heck that means. So odd multiplicities means that we have a point of inflection on the x-axis. That's when our power is greater than or equal to 3. Okay, if the power is 1, it's going to be linear. It's going to cut through. But if it's a power of 3 or higher, it's going to flatten, and that's going to give us a point of inflection there. So do you see any point of inflections or flattens on this graph? Oh, you do? Awesome. At x equals -1. Perfect. So it's that first blank right up there. So x equals -1 has multiplicity of 3 with a point of inflection. If you're ever wondering, well, Coach, your handwriting is just fantastic. How do you do it? It's because when I'm making these videos, I'm actually writing upright. I'm writing onto a surface like this. I'm not writing like this, so that you can see, so that I can have a webcam here in case I need to make any visualizations. All right. Non-real zeros. We don't talk in AP PreCalculus too much about imaginary numbers. We really don't. That's different from previous years with advanced PreCalculus. But what we do need to know is if we have imaginary zeros, that its conjugate is also imaginary. So if we ever have a imaginary zero, and you might be thinking, like, how do I have imaginary zeros? Well, let's talk about our linear factors. Let's say that I have some function here, x minus 2. I used that before. And then I have x squared plus 1. Okay? Well, for the zeros, I just set each of these equal to 0. And so for that first linear factor, first factor is called a factor, you get a nice clean number, you get 2. For the second one, x squared plus 1 does not equal 0. If you actually solve for that, you would get a complex number, which is something you learned in Algebra 2. So you should know some of the stuff from Algebra 2. So whenever you have one complex number as a root, you have a second one because the conjugate's also going to be a root. So that's all that's saying. And what's a conjugate? Well, real quick, if I have 2 plus I is a root, as just as an example. This is different, by the way. This is not relating to the f of x. If 2 plus I is a root, that means 2 minus I is a root. Those are conjugates. Conjugates just have different signs in front of the imaginary number. That's it. Those are conjugates. So here's our example. We have some really unknown polynomial function that's degree 3. We have ax cubed plus bx squared plus cx plus d. We know something. We know that x-intercept is 1.7, comma 0. And we know that 2.3 minus 5, or I can't talk, 1.5i is 0. What do we know about the other solutions? So we should have 3 zeros. We have x equals 1.7 because they told us that in the problem. We also have 2.3 minus 1.5 I. We're missing 1. Okay, didn't talk about multiplicity whatsoever, but I know we're missing 1. What is our missing 1? Well, we're missing the conjugate. So we are missing 2.3 plus sign in front 1.5i. Okay, that's it. Let's talk about odd, even an odd polynomial function. So we're kind of throwing a lot at you here. We're kind of just throwing in roots and multiplicities above here, throwing in imaginary stuff. Now we're going to talk about even odd. We're just kind of throwing a lot at you here, so I get it if it's like what's going on, what's sticking here. These are all, I would say, fairly simple concepts. It's just putting it all together into one package, so it could kind of seem like we're jumping around a lot. But these all relate to polynomials, what we're trying to do here. Okay, even and odd polynomials. This is different than even degrees and odd degrees. An even degree function may not be an even function. An odd degree function may not be an odd function. So please be aware of those two different things. Even degree talks about the highest power being even of a polynomial. Odd degree is the highest power exponent of a function that is odd. Even function is completely different. This is what it says, that even function is graphically symmetric over the line x equals 0 and has an analytical property of f of negative x equals f of x. So this is what that means. So for evens. And I'm going to draw it down here. If I have a function that looks like this, and I tell you this function is even, that means it's going to reflect over the y-axis, which means it's going to look exactly the same. Okay, so that's how you mirror that over for an even function. Okay, so even functions fold over the y-axis. Okay, that's an even function. Let's talk about odd. Odd functions are graphically symmetric, okay, which has the property of f of negative x equals negative f of x. So if I were to kind of draw the same thing here, I can't do it because I don't have a piece of paper in front of me, but the easiest thing to do is to just rotate the piece of paper, and then it would look like the exact same thing. So really, it would look like this right here. So essentially, if you look at my blue dotted line and my pink dotted line, I just flipped it over the x-axis. Okay. You know what? I'm going to kind of give that another try because I don't know if that's super clear for you. All Let's just watch me erase. It's so fun to watch me erase. Okay, I'll try to do it like this. That way you can tell a better difference. Okay. Maybe that's a bit more clear. They get the heights a little bit different. Okay. So let's talk about how to mathematically find this out if we don't have the actual graph. So let's go ahead and do that for the first one right here. So find out if we're even or odd. All you're going to do is plug in a negative x into the x. So for number one, didn't really leave you a lot of room here, but we're going to test p of negative x. If I throw in a negative x, I'm going to get 5 negative x all cubed. And all we got to do is just one step of simplification. If it matches, we're even. If it's complete, every single sign changes, we're odd. Neither of those things happen, then we're not even or odd. So if you have negative x cubed, any negative number that's being cubed is still negative. So this is negative 5x cubed. Which, by the way, this looks almost exactly like the original p of x. The only difference is it's negative, which is perfect. Saying that this is going to be odd. Okay. Oh, I forgot to mention down here in my little graph. Let's label this as odd. Okay, let's go ahead and go to the next one. Number 2. All I'm going to do is plug in a negative x. If I could do this right. So plug in a negative x. So every single x term I see, I'm going to plug in negative x. So I'm going to get 5 negative x to the 4 plus 2 negative x squared, which being negative x, it doesn't look very negative-y. And then minus 6. Well, what are all those even degrees do to those negative x's? They actually make them positive. So this is going to equal 5x to the 4th plus 2x squared. And that 6 didn't change at all. That looks exactly like f of x. So we're going to say that this is even. Okay, let's go to our last one. Let's pick a better color. All right, I tried picking a different color and I'm having technical difficulties. This is what I get. You'd think I would just remake this video, but at this point, so far down the road, I'm not going to do it. I have to remind myself not to touch the eyedropper. Okay, technical difficulties. There we go. Let's change out the yellow for a red. All right, got a red color now. Okay, so for now, for number 3, try this one on your own. Put it right here. Try number 3 on your own and see what you get and see if we match up. I would advise you hit pause and then see if we match up. Okay, welcome back. So we plug in a negative x into g here. We're going to get 4 negative x cubed plus negative x. That negative x being cubed is going to pull that negative out in front. And I can actually factor out a negative right in front of that so that I can match my original function of g. If you look, this does match, just with a negative out in front. So we can say that this is a odd function. All right. So this note's pretty heavy. We got 4 different concepts going on. We're talking about multiplicities with roots. We're talking about conjugates with imaginary roots. Now we're talking about even odd functions. And our last one here is using tables, which is pretty heavy concept here in AP pre-calculus. I will apologize ahead of time. There's not a lot of room to do all the stuff I want to do here. So I'm going to squeeze it in. Hopefully I explain it pretty well. Okay. Finding the degree of a polynomial, if you're just given certain values, we're given values in terms of table, which makes it pretty easy for us. But we're going to look at rates of change. That's all this entire box right here is talking about is rate of change. If the first rate of change is all constant, then we have a linear function, which makes sense. That means that the rate of change, no matter what 2 points you pick, always the same linear function. If the second difference is constant, so the first difference is not constant, and then we keep going, the second difference is constant, then that means that we have a quadratic. That means that the rate of change of the rate of change is constant, which is really talking about concavity as well. If we have a third difference is constant, that would be a degree 3. So that'd be the change of the change of the change. Okay. And that pattern continues for any other degrees going further. Okay. So for number 1 here, I'm going to try my best not to make any typos because I really don't have any room to make typos. Okay. What I'm going to do is I'm going to find the change in x, make sure that's constant. If the change in x is constant, I said x. If the change in x is constant, then I'm good to go for change of y. If not, I have to be careful, make sure that my change in x and change of y is from one point to the next match. Well, if we look out right here, we're going up 1. I put a +1, by the way, for these just to help me out. These are all +1s. So there's nothing tricky going on. I don't need to divide my other differences by 1 because, well, they all would equal itself. Okay, so the difference from 5 to 2 is going to be -3. The difference from 2 to 1 is going to be -1. The difference from 1 to 2 is going to be +1. The difference from 2 to 5 is going to be +3. Okay. Are those differences constant? No, they're all different. So let's go to the next round. I'll do the next round. Why is white even an option? Next round is blue. Go from -3 to -1, +2. Go from -1 to 1, +2. Go from 1 to 3, +2. All of those differences are constant. So that's the rate of change of the rate of change. And what I would do here, and maybe make your life a little bit easier, is to kind of like label these. Okay, this is degree 1 right here, not constant. This is degree 2 right here. 2 is constant, so our answer here is going to be degree 2. All right. Isn't that so fun? Sure is, coach. Oh, yeah, no, I agree. Okay. Let's come back over here, number 2, and then I'll have you try 3 on your own. If I'm looking at my change in x's, oh, by the way, these all represent change in y. Okay. All the reds do on that other side. Change in x, these are all constant. And I just check this. You never know what kind of question you're going to see. Make sure that that change is constant. If it's not constant, then you need to do change in y over change in x. Okay, let's go ahead and do the first change in y. So from 5 to 2, that's going to be down 3. 2 to -1, down 3. -1 to -4, down 3. -4 to -7, down 3. That is all constant. So what can I say about number 2? This is degree 1. Okay? All it is asking us to find the degrees. Now you're going to try number 3 on your own. You're going to pause this and see how you do. Oh, welcome back. All right. You should have this all done and hopefully you have the answer. If you notice here, I'm freezing. All of my change in x's, super convenient, changing by 1. I like to check it. It's what the cool kids do these days. They all change what I want. That handwriting looks awful. Those all say +1s, by the way. I'll do better. Change in y. Okay. From 26 to 7. Big one, but I got going down 19. 7 to 0. I got going down 7. I got going down 1. I got going down 1. Okay. Let's do the next color. Let's do, those changes are all not the same. I got going down 12. I got going down 6. I got going down 0. Those changes are not constant either. From -12 to 6, I'm actually going up 6. -6 to 0, I'm actually going up 6. Those are constant. So this is degree 1, this is degree 2, this is degree 3. These match up here. So our answer is degree 3. This is a long video, so I am going to get out of here. Make sure you like and subscribe.